Hello once again, AP Calc BC students. Mr. Record here from Avon High School, and we're going to take a look at our last example from what basically serves as a review topic going into the basic components of Unit 7 in College Board courses and description for calculus. So at my school, we do basic calculus as a second year course for our AP, just to give my students a little bit of a refresher over differential equations. We talk about basic differential forms, we solve them, and then we work one application problem. And this happens to be that particular problem. It's got a little bit of a historical kind of vibe going on with it, as we're going to date a religious artifact. So let's take a look at our problem. It says in 1988, the Vatican authorized the British Museum to date a cloth relic that was known as the Shroud of Turin. And I have a little picture of it over here, as you can see. It says this particular shroud was possibly the burial cloth of Jesus of Nazareth. And the cloth first surfaced in the year 1356. And as you can see from this image, it contains the negative image of a human body that was widely believed to be that of Jesus. The report of the British Museum showed that the fibers in the cloth contained between 92% and 93% of their original carbon-14. And we know that carbon, which is the basic building block of all organic things, is going to have a half-life of 5,730 years. What we want to do is basically use this information to estimate the age of the shroud. And what's really neat about this problem is that the technology wasn't around to carbon date so accurately prior to this particular time period in the late 1980s. They could do it, but it wasn't going to be nearly as effective. And so it's very cool that, just like sitting there in front of your mobile device or computer watching this, you have the capabilities of doing this. All we're going to need is a graphic, or at least a scientific calculator, to pull this off. So radioactive decay is a big application of differential equations. And the thing that we have to remember about radioactive decay is that it's always set up so that the amount of a particular substance is going to decay at a rate proportional to the amount of stuff that's there. Now, what does that mean in this particular problem? Well, I'm going to use y to be just the very simple variable that stands for the amount of carbon. I could use c. I just kind of want to stay away from that because of the constant c. And so by using y, I think I'm going to use a very familiar variable for you. And so t is going to be measured in time, it's in terms of years. And we have the information that use radioactive decay that says that the rate of change of this carbon with respect to t is directly proportional to the amount of the carbon. So that's dy with respect to t, derivative of y with respect to t is k times y. Now, some of you may be sitting there thinking, well, hey, I know what this is going to do. When we solve this equation, it's going to give you y equal our familiar friend kect, as we like to call it at my school. But if you had forgotten that, it takes about 4 steps or so to develop that. And so I'm going to review that with you in case you need to see it. But we're going to separate these variables by dividing by y. We're going to move the dt over. Effectively, it looks like we're multiplying the dt over. Not really what we're doing, but for right now, we can move it in that particular light. We're going to take basically look at the left side with respect to y, and the right side with respect to t. Now, if we go ahead and integrate, right? If we integrate both sides, we're going to get the natural log of the absolute value of y on the left, and our typical k times t, plus our constant that I'm just going to call c for right now. Now, all we have to do at this point is solve for y. We don't have a specific c that we're going to be able to use. We don't quite have an initial condition per se. We're going to worry about finding k later on as well. But that's okay, because we can solve this for y if we exponentiate both sides. Of course, the e and the ln will kind of do away with each other. We have the absolute value of y equal to e to the kt. Now watch really carefully what I'm going to do to this right side. Instead of having a sum in my exponent, I'm going to exercise a very common property of exponents and allow myself to multiply by two like bases of e, where those two exponents of e would essentially be added if we were going back that direction. That's going to be a really common maneuver that you use when you solve these kinds of problems. All right, so next up, we're going to go ahead and recognize this e to the c as being a constant. That's all it is, right? And what I'm going to do is, so as to not confuse this constant with the constant of c, let me give it a different subscript name, like subscript of 0 works really good for me. Now, you don't have to call it subscript 0. I like to do that. I'm going to explain why in a second. And the beautiful thing about this is that you could conceivably get rid of the absolute values. I know sometimes this confuses students, like, whoa, how do we know that we can get rid of the absolute values? We don't know what the sign of the right side is. Well, that's the beautiful thing about this constant. It can be a positive or it could be a negative. So all of that could be absorbed into this CO. And so I'm just going to leave it at that. And there it is. There's our familiar y equal kect, right? CO will always stand for the initial amount of this radioactive substance, carbon in this case, and K is always going to be this constant that applies specifically to this particular type of cloth, the cotton fibers or whatever the plant is that basically makes up the fibers of this particular cloth. So we have a little bit more work to do, right? You know, even though we know that y equal kect is going to be our main formula, we got to do some things, and we're going to actually go about finding the value of the k. And you can always do this in a very typical fashion. Because we are talking about half-life problems, you don't really have a specific beginning amount or ending amount of your carbon elements here. So what you can do is make up any pair of numbers in the world that have that half relationship. I could make the initial amount 25 and the ending amount 50. I could make the initial amount 47 and the ending amount 94, right? As long as the y is double that of the CO, all is good, because it doesn't matter, because we're going to divide the CO over anyway, and we're going to get a 1/2. And you know what, guys? I think I have that backwards. The CO is bigger because this is decay. So let me explain that again. I could let the CO be 50 if I wanted to, at which point the y would be 25. Let that sink in, because I did explain it incorrectly. I could let the CO be 2 and the y be 1. Well, doesn't that make the most sense? Because if I divide that 2 over, I'm just going to get a 1/2 over there on the other side anyway. And notice all of that is going to happen. I'm going to have this half-life relationship when the time, is 5,730 years. And now you have an equation that you can solve for k. So like I said, we're going to divide by 2. And I might bring out that 5730 in front of the k. Now, the next couple of steps are going to be just a review from pre-calculus. So we're going to take the natural log of both sides. Note that whenever we take the natural log of a base e, let me get this powder correct, of a base e that has an exponent attached to it, we can utilize the power property for logarithms that says that this exponent can be multiplied out in front of the natural log. So we'd have natural log of a half as 5730k times the natural log of e. And at this point, some of you might even be astute enough to say, well, I'm not going to write down the natural log of e because it's just equivalent to 1. And so it's essentially going to go away. And then when we solve for our k, and if we want to leave this as precise as we possibly can, you could say that it's natural log of a half divided by 5,730. And I tell my students that that's really what I would like you to do. I would like you to keep this k as accurate as possible. Let's not go down the decimal road until the very end of the problem. I also want to make sure it's clear, and I don't know if anybody would have been thinking about this, but the natural log of a half is also negative natural log of 2. Yeah, I'll let that sink in for a little bit. How is that possible? Well, the natural log of a half is like the natural log of 2 to the negative 1 power, right? 1/2 is 2 to the negative 1. And remember the rule about the exponent coming out in front. And so it's just another way to write it. Whether you think it's better looking or not, that's really entirely subjective. So we're on our way, guys. We have this value of k. That's going to start getting things moving for us here as we start to figure out how old is this shroud. Now, the report from the British Museum had showed that the fibers in the cloth had about 92 to 93% of their original carbon-14. And so what that means is the ratio would be that 92% if it was on the low end. What does that mean with our Keck equation? Well, how about we use 100 for the original amount of carbon? Now remember, we don't know how much carbon was in it, but it's all a ratio, so it really doesn't matter. We can literally make up our own numbers as long as we have this percentage. And so if 100 was to start, 92 is what would be at the ending of that during this analysis that focuses on the low end. I'll show you what we're going to do at the high end here in a little bit. And so we've got those two as our Y and our CO, right? Don't forget, we've already figured out that our K is 5,730, right? I'm sorry. Our K is the negative natural log of 2 over 5,730. And then that gets all multiplied by our time t, because that's what we don't know, right? We don't know the time that it takes in order for this particular cloth to decay to that 92%. Well, we're going to divide by 100, which obviously is going to give us the 0.92. And then we have this e to the negative natural log of 2 over 5730 times t power. Now you might wonder, well, what the heck are we going to do with that? How do you solve an equation that has a variable in the exponent? We're going to take the natural log of both sides. That's really about the only way that you can do, right? That kind of an equation solution. You're going to have to use logarithms to solve these pretty nasty equations that have variables in the exponent. Since calculus deals so much with the natural world, the natural log does the best job for us. And so once again, there we go. I'm going to make sure that you're all reminded that this expression here is all the exponent. So I'm going to put parentheses around that to kind of highlight that, because once again, I want you to all see that you have the natural log of e to an exponent, which means that exponent, by way of the power rule, can move in front of the natural log. And so you have ln of 0.92 on the left. You're going to have negative ln of 2 times 57 over 5730 times t on the right. And that ln of e, I'm not going to even put on paper here because we know it's going to be equivalent to 1. And so then if I divide both sides by negative ln of 2 over 5730, or better yet, multiply both sides by the reciprocal, I will have an exact value that will depict the time that it took for this particular item to decay to that 92%. Now, what I want to do is kind of play the role of a scientist here, and I want to err on the side of the greater amount of carbon at 93%. And so essentially, we are going to replicate this entire process, which I know you're thinking, oh no, we're going to do the same thing, except of course now the natural log on the left side would be of 0.93. Everything else is the same, right? And so we know that this is going to be our low end, and our high end is essentially the same thing, but just really change that 2 to a 3. And this is going to be our time frame, right? We know that the age is going to be somewhere in between these two values. And maybe I'll call this T1 and T2, okay? Now, I know it's like, well, gosh, these mean nothing to me, right? Well, of course they don't. And this is where the calculator is going to come into play. And any calculator will work as long as you have a natural log button. So we're going to use a TI Inspire here. So let's go ahead and I'm going to resize my window here a little bit to make this just a little bit prettier. How's that? Hopefully that works a little bit for you. And let's type in our low end expression. So I think we have natural log, so that would be Control LN, 0.92, right? And then we're going to multiply that by, the fraction. And remember, we use the reciprocal. 5,730 is going to be over negative natural log of 2. And this should give us some nice decimal output. And so we get 689 and a little change there. Now, we start to kind of see something here. If you think about what the original problem said, and I'll return to it here in just a moment, but it said that this cloth first surfaced in the year 1356. And if that were the case, then about 700 years prior to 1356 would have been the year 650s, right? The middle of the 7th century. And according to the calendars that we've kind of adopted during that timeline, we would say that this would have had, if this were going to actually be the burial shroud of Christ, is that it would have to be about 1356, 1326 or so years old, right? And so it's dating much too new for that. And then I'm going to do the same thing. I can simply highlight and enter the same expression, or I could retype it, and we're going to get the larger end here, which is about 100 years later, but still it's not going to work. According to our estimate, we're going to have a range of these two values. So let me drag my calculator screen in here so that I can see those numbers. And let's adjust my window so it looks a little bit more attractive here. All right. And so what we've determined, use this information to estimate the age of the shroud. Well, we're going to say that the shroud is between, and I guess if we want to be very, very good AP students, let's go ahead and round this to the 3 decimal places. I would probably say that that's overkill for a problem like this, and I would say you could round to the nearest year. But let's go ahead and keep with the spirit of the exam. So the shroud is between 599.916 and 689.286 years old. And as I said before, if either of those are subtracted from what the British Museum was saying from the time that it first surfaced, it can't possibly be the shroud that would have been dated around 0 or 30 AD in this case. So debunked at this point. And I think the story has been released back in the 80s that this particular artifact, by all scientists who have investigated it, is not the real deal. But it's great to kind of use mathematics and calculus in general to take a look at a very interesting piece of history. Anyway, I hope this helps out, and as always, keep studying your calculus, and we'll see you next time.